participant, and now I'm involved in the organization of IYPT, currently as treasurer, and I'll be chairing today's fight. I would like to start with a brief introduction round. Can we start with the teams? Because you guys are the most important people here. So may I have the reporter quickly introduce your team.
Okay. Hello everyone, I'm a captain from Team Taiwan, and this is Oscar, this is Justin, this is Andrew, this is Kai, and you can call me John, and we hope to have a great fight. Thank you.
Thank you.
Hello, we're Team Austria, and I'm here with my teammates Noah, Gabriel, David, Anna, and me. I'm Lamia, and also our mascot Lisa. Thank you very much, and we wish everyone a nice
And the reviewing team from New Zealand.
Hi, I'm Jason. I'm here with my teammates Julia, Alan, Caden, and Audrey, and I'm here with my mascot, Best wishes everyone.
Okay, then I would ask my colleagues in the jury to give a brief introduction.
My name is Josephine Sjöholm, and I'm a high school teacher in physics since 25 years. Good luck to everyone.
Hello, my name is Mladen Matev. I'm a doctorate researcher in physics and nuclear physics from the Bulgarian Academy of Sciences. I've been with the IYPT since 2004 at various levels. Team leader in 2014, and then since 2018 as an independent juror. Wishing you all good luck.
Good morning, my name is Tomasz Gryczyła. I'm from Poland. I'm also an independent juror involved in the IYPT like a decade already. I'm a university professor and also a teacher at the high school, so I wish you a good competition.
Hi everyone, my name is Luka Bulaya. I'm a PhD student at the University, I'm from Serbia. I'm a PhD student from the University of Belgrade and the University of Turin. I'm involved in particle physics, also in a promotion of science and stuff like that. And I wish you good luck.
Thank you. Okay, the procedure is slightly different. We already selected the problem. Yes, 1 minute. Yes, 1 minute. The preparation phase is 1 minute. So whenever you're ready, we will. If there are no questions from your side, I think we can start with the actual fight. So, all right, 1 minute for the report. It's not implementing the clock, but it was voted on last IOC's meeting, but it's still good.
That sounds fine.
Hello everyone, I'm a reporter from Team Taiwan, presenting problem number 14, water bottle rocket. I pump air into a plastic water bottle partially filled with water. Under certain conditions, the bottle can be launched, and I have to investigate how the acceleration here and lift off depend on relevant parameters. For the bottle parameters, it will be a bottle volume, shape, and also diameter. And for the fluid and launch parameters, we'll have the inside pressure, water volume, and launch angle. Here are the contents for today, and I'll start with the launch process and our observation. So I pump air into my bottle using an inflator. And this high pressure air will push the water out in a high flow speed. And due to the conservation momentum, as the water is coming out, the system is expelling mass. So it will generate a thrust force to compete with gravity and drag. So here is the observation. When I remove the plug, I see 3 phases. First, we'll have the water jet. Then we go to a mixed exhaust. Finally, the air jet. After this, it is the end of liftoff. We have to find as there will be no more acceleration. And here are the in-scale times under these parameters. I also track the acceleration over time for my water bottle rocket, and I see it will first increase then decrease. I believe the increased part is due to the water jet, the decreased part is a mixed exhaust. The air jet affects minimally under these parameters. Now, let's go on to our lift-off model. This is the ideal rocket equation, while it assumes V exit is constant. This is the generalized ideal rocket equation, where I put in some modification of gravity and drag. Compared with the results, we find it does not match the experimental results theoretically, because in a real water bottle rocket, V exit will change with the pressure over time and mass over time, as it will be different from a normal rocket. So, write down a new equation of motion for a rocket with the thrust force, gravity, and drag. For drag force, we govern using this equation, while the coefficient can be solved using computational fluid dynamics, where I've solved flow 3D in the Navier-Stokes equation, where I was able to find the coefficients under different velocity. Then, for force, it will depend on different stages. So we'll have a separate theory for the water jet, mixed exhaust, and air jet. So for a water jet, based on the conservation momentum, we could derive the thrust force into the mass flow rate times exit velocity. So we write down the mass over time, as the mass of the bottle will be the total mass minus the flow rate over time, which is m dot. As we consider an inlet loss due to turbulent conditions in the bottle's geometry. Then, for the velocity, here we write down the Bernoulli's equation for a water jet velocity. As we simplify using a continuity equation to get the V exit, considering for the static pressure and the bottle nozzle ratio. Finally, for the pressure over time, we're assuming as a polytropic process, as PV gamma equals to constant, the gamma will be between 1 and 1.4. And we can write the pressure over time with this equation. We'll solve the mass over time, velocity over time, and pressure over time with the differential equation shown over here. Then for mixed exhaust, we see from the picture, some air will get exhaust out with the water, as it will form a spray-like exhaustion. So we will slightly modify my flow rate to have an effective density, which we define as the water and air volume ratio. The air will flow out normally in a Bernoulli's equation. However, at the same time, air will flow out in a subsonic flow rate. So we'll calculate the volume ratio between the water and air to obtain the effective density. Then for air jet, we'll neglect air's momentum due to a small density, so it will just be area times pressure difference. As I experimentally find the air rocket is still possible, as there will be no water in this rocket. Then we can write down the pressure over time with the ideal gas law times the mass flow rate of the air. Now let's characterize some parameters and investigation inside our bottle. So here's my static launch setup. So I confine my bottle onto a stand, so that way I could put a sensor inside the bottle to see what's happening inside. So the goal for this is to characterize my coefficients and to compare to the theory individually. Thus, I can get the thrust over time and energy dissipation ratio. So for my bottle, it is a 600 milliliters soda bottle, where I will have nose, nozzle, and 4 wings. I have tracked the edge of my bottle and fitted a curve onto it, so I could get a better volume profile of my bottle by integrating inside. So to determine index gamma, I will have to measure the pressure and volume over time. Then apply a log-log fix for the pressure and volume to get the slope, which we find that gamma is 1.15, as the process will be slightly closer to the isothermal process. Then, to determine inlet loss, I prove this is true because I have tracked the red beads in the middle and the side. As we see, they started off with a very similar velocity, but after the bottle radius starts to shrink, the velocity is different. This is a constant loss due to the geometry of the bottle. And I calculate this by comparing the experimental and theory flow rate. And the orange dots are the measurements. And we find the C loss equal to 0.71 with this blue line. Now, we will compare the pressure over time and air volume over time. When C loss equals to 1, we see the theory pressure will drop too fast, and the air volume will increase too fast. But after getting the determined C loss equal to 0.71, we will get accurate pressure over time and air volume over time. Then I investigate the thrust force over time as I tie my rocket onto a force sensor. And I compare different nozzle cases. And I adjust the nozzle size by adding clip. And we find for a larger nozzle case, we see a higher thrust, but the water will run out very fast. And for a smaller nozzle case, it will drop down down more steadily. This way, I could get the energy dissipation ratio, as the three components I've considered is the adiabatic heat loss, fluid loss, and air draft. Under these parameters, we find the adiabatic heat loss being the most dominant, then the fluid loss and air draft is the smallest. Now, let's investigate the acceleration over time for my rocket. Here is my free launch setup, which I use a 240 FPS camera to capture it, as I have considered the parallax of the rocket. Then, for acceleration over time, I'll be investigating the inside pressure, water volume, and launch angle, as the other parameters require a bottle change. And I'll plot the phase diagram on the launch conditions on when would it launch and the stability analysis for my rocket. So here's my raw data for acceleration over time, as I'll apply a 5-point moving average to slightly smooth out the curve to compare with the theory. And for my theory, I'll have two phases. I'll plot the water jet and mixed exhaust. After mixed exhaust, it will be the end of liftoff. The cutoff region can be determined using the video, as we can see a very obvious spray-like transition. And also, we did not plot the air jet. It's because in ovine experimental range, the air jet affects minimally, as the air jet is only significant in air rockets. So here's the first parameter of the initial pressure. Here is where we go up the pressure. As you can see, if the pressure increases, the end of the thrust will be earlier, and we will have a maximum acceleration. This means it will have a higher burst. This is because the water will exhaust out in a higher rate due to a stronger push from the high pressure. I also integrated below the curve using Euler's method. And we find the maximum height will be increasing with the initial pressure. Then is the water volume. So we see for the yellow case, it is a smaller amount of water. We see a sudden big thrust force, but the acceleration time is shorter due to it will run out of water very fast. Then for more amount of water with this green case, we see a larger acceleration time, but the maximum is not as much due to the heavier mass. For a purple case, where the initial water to air ratio is too big, the volume of air will increase a lot. So the pressure will also drop a lot, causing a very, very small acceleration curve. And I find the maximum acceleration is where 200 milliliters, which is around 33% of the water volume, where I was able to estimate and find 33 is the actual volume. Then the problem statement mentioned under certain conditions. So this is a phase diagram of initial water volume and initial pressure. The red part is where condition where a rocket doesn't launch. Then these regions are the rocket launching. The blue region means the rocket is launched but not fully exhaust. From video, we can see it will launch off, but some water is still remaining inside. So if you want a launch and fully exhaust rocket, you need a higher initial pressure or lower initial water volume. Now let's look at the launch angle. So I slightly modified my theory to have an x and z direction component. We see from the data, it will start out very similar. But if your rocket is closer to the ground, we see it will have different exhaust times and deviates a lot. This is due to the water level will cause the peak time deviation. When a rocket is very tilted, the water level is closer to a nozzle, so it will be easy if decreased over a nozzle and start to have the decay. So I run a new simulation as considering the tilted of the water level and when it will surpass the Y nozzle. And the dotted line are my theory prediction, and we can see the new prediction are better with the solid line, which is the experimental decay time. Now, when conducting the experiments of a tilted rocket, I also find a phenomenon where the rocket stabilizes itself. This is due to a torque acting on the rocket. So this is because the position of the central pressure is below the central mass. When this happens, the draft force will stabilize the rocket. And the opposite will happen when the position is opposite. So the final parameter is I will add clay onto a rocket to vary the central mass. So for the flip region, I define as the rocket is more than 90 degrees. And we can see from the video, the rocket gets completely turned over and starts to accelerate downwards. So when you move the mass point movement downward, you will go from successful to unsuccessful due to the torque is bigger, causing it to flip. And when you increase the pressure, you will go from failing to successful due to the water can exhaust out fast enough before flipping over. Now, in summary, the thrust is generated by the conservation momentum, as I have a three-phase thrust theory with a CFD drag simulation. And for launch experiments, I was able to determine the curve of the bottle and find pressure over time and volume over time with the gamma equals to 1.15. Then I was able to determine the C loss equal to 0.71. So the energy dissipation can be calculated as the adiabatic heat loss is the most dominant. Then for the acceleration over time, I've investigated the initial pressure, launch angle, and water volume, as its relation is shown over here, and it will reach maximum at around 33% full. I've also plot a phase diagram for launch conditions and rocket stability. The final question is, what is the difference between a water bottle rocket and an ideal rocket? The similarity is the conservation momentum. The difference is when a water bottle rocket, the eject velocity will change over time. And this is the end of my presentation. Thank you.
Thank you. Question from the opponent.
Thank you for the presentation. Did you consider the nozzle radius
Yes, in my theory.
in your
Yeah.
cell parameter? Did you vary it in your experiments?
Only the thrust force over time.
Okay. Thank you. For your setup, like I saw you had an acceleration diagram, and this was for a ground-based setup, or for the lift. Did you have a lift off?
Yeah.
Yeah. Okay. And at this lift off, how was the release mechanism? Was it a sudden or controlled?
It's can you? I don't. What's the?
Was it a controlled lift off? Because if you pump pressure into the bottle,
I could release it when I want with a handle.
Okay.
Yeah.
Okay. Thank you. Okay. So just how did you? Okay. How often did you repeat your experiment? So for the error analysis, did you see any difference? In your
Five
experiment?
times.
5 times. Okay. Did you consider the temperature of the water or of the bottle?
I have measured it, and it will around. Let me try. Oh yeah, this one. It's around like 2 degrees difference.
Okay. Okay. Thank you. And for the polytrophic coefficient gamma, how did you determine it experimentally also?
Yeah, experimentally. I measured the pressure over time and volume over time, and think a lot like it.
And did you think that temperature change in the bottle has an effect?
So that's why we find it to be 1.15 and instead of the
Need to
constant temperature.
Okay, thank you. Okay, next, what were the maximum pressure that you could insert into the bottle?
Maybe 3 ATS.
Okay, thank you. What were the limits of your bottle?
Limits of my bottle?
Yeah, for the volume and...
Oh, it's 600. Yeah, here, it's 600 milliliters, and I've tracked the edge of the bottle, the curve.
Okay, thank you. Did you consider friction inside of the bottle? Like, I thought you had, due to the geometry of the bottle, but
Yes.
like on the wall of the bottle.
I think it's considered in the C loss, like it is turbulent, yeah.
Thank you very much.
everyone. My name is Gabriel Hegi from Team Austria, and today I will be opposing problem number 14, water bottle rocket. So first, let's read the problem statement. We already have seen it. So pump air into a plastic water bottle, partially filled with water, and under certain conditions, the bottle is launched and flies into the air. Investigate how the acceleration during the liftoff depends on relevant parameters. So for the theoretical approach of Team Taiwan, we had the conservation of momentum as a qualitative explanation of the phenomenon. So the liftoff was in 3 phases, like we had the water jet, the mixed exhaust of mix of water and air, and also only air jet. They used the Tsiolkovsky ideal equation of rocket, which we believe is not sufficient. They had the thrust force equation, which also depended on the nozzle radius. The Bernoulli equation for the water jet velocity, which I would like to discuss in the discussion. And they considered the process as being polytropic, which we agree with because it can definitely not be adiabatic. Also, they investigated mixed exhaust of air and the air jet, and the volume profile of the bottle was tracked via tracker. And also the energy dissipation was considered due to the temperature change and dissipation of energy. For the experiments, they had an inflator for the pressure, and they had an acceleration over time tracking and not on the ground setup. They had a determination of the inlet loss by tracking of in the bottle itself of the red beams. The pressure and air volume were varied over time, and also the thrust force was varied. They compared the 2 phases, and several parameters were investigated which we think are relevant, like the initial pressure, the water volume, and the launch angle. Also, the stability of the rocket was investigated, and they had some adjustments like a nose cone or some fins on the side of the bottle. So for the positive aspects that we liked about the presentation and the theory was the polytropic consideration, and that they considered air drag, which we think is very important for this problem, because we have high velocities and high accelerations at the beginning. Also, they considered the mixed exhaust of air jet and also water jet, and included this in their theory, and volume of profile of the bottle was tracked. Also, they used the Navier-Stokes and via flow 3D. But for the points they improved on, it was not really clear how they elaborated the drag coefficient. Like, was it experimentally or just theoretically or from literature? I would like to talk about this later. Also, the friction analysis was a bit unclear, but I think very good, very precise. For the experiments, they had a pressure sensor in the bottle, and I would like to talk about this later also. They had the inlet loss determination, and also encountered for the parallax error, which is very important if you have the setup that launches into the air. Also, they did some stability analysis. For the release mechanism, it was a bit unclear. Like you said, it was you could do it when you wanted. I would just like to talk about this later. It had a bit of lack of error analysis. Like I couldn't see some big errors analysis in your graphs, and you did not vary the nozzle diameter experimentally, if I got this right. So for the points of discussion on, if we get back then to the Bernoulli equation, I would like to talk about the G effective, which I think was not included in the equation, but we'll see that later. Also, just the pressure equation, so the theory and all, and also the air jet for small water volume, because we think that if we have only small water volume, then there's also air jet coming important. So further parameters to determine, and the air drag and the friction inside of the bottle. Thank you. I'd like to now invite the opponent to discussion. Okay. So for could you maybe get back to the slide where you have your pressure equation? I think it was Bernoulli, right?
Yeah.
Yeah. Okay. Thank you. So you have this G term here.
Yes.
Don't you think you need to have a G effective term
Oh yes.
due to the acceleration?
Oh yes. Are you mentioning like this G needs to be the condition, the G effective while it's launching off?
Okay. And okay. So, but actually, from this pressure, did you determine the acceleration?
We could calculate acceleration using
So use the pressure equation then, and from these results you used to calculate the acceleration.
Yes.
Yeah, and I just don't understand, how can you have the G effective in your pressure equation, but then later use it to calculate the acceleration?
No, this is a normal G. This is not a G effective.
Okay, but don't you think it should be the G effective in the pressure?
I do agree, but I think it is affecting minimally because if you if you compare like the ratios of this static pressure term is actually quite small.
It's actually quite small. Okay, thank you. And for the acceleration, like the problem statement is about the acceleration. What were the max acceleration reached with your bottle set?
It is around. Let me see. Let's see, is around like 400.
And you think that this is a small acceleration?
Well, what do you mean?
So, this, like, don't you think that this is an acceleration that has to be considered in your G effective?
Oh no, but I mean the H term is quite if you were to calculate it's quite small.
Okay, thank you. Okay, so just for like you said that air jet. Yeah, I like that you included your air jet theory, like only air getting out of the bottle, this phase. But what do you think if you have small volume of water and you launch off? Doesn't really fast then the air get out. So don't you have to consider the only air jet also in the acceleration? If you have small water volume.
But I have the mixed exhaust. So are you talking about like the changing of water volume?
Mm-hmm.
Yeah, because the pressure isn't pumped that much inside. So after the mixed exhaust, the pressure difference is basically zero.
It's basically
yeah. So this is the mixed exhaust. So with the air and rocket going out at the same time.
Okay, so you did consider this in theory. Okay, thank you. Okay, and so only for the friction inside of the bottle, could you elaborate on that? So it was just due to bottle geometry that you considered the friction on the bottle.
Yes, it is experimentally determined in the C loss.
Okay, but and don't you think that the bottle itself, if you have water volume, big water volume is has to be considered like on the walls of the bottle? Don't you think this has to be considered? Like
yes, but yeah, I mean it is determined in the C loss. Like I think the C loss in all the equations are 0.71, and we see
it was for the overall.
Yeah, I think it's
shape. Okay. Okay, thank you. And the air drag coefficient. Let's get to this. So actually, we have very high velocities as I expect for this experiment.
Yeah.
So how did you calculate it via this Navier-Stokes? Right?
So it is in the software. So you can imagine I just set the rocket in the same place and add like a wind tunnel in the simulation. I went for it and I could
Did you compare it to your experimental setup? Like
I did not experimentally determine the coefficients. I just run Navier-Stokes. Yeah.
Okay, thank you. Okay, but if we get to the mixed jet, how can you explain it? Because actually we have some the air and the water, and it varies between air and water. How did you qualitatively explain this mixed air, mixed air and water?
So it is a condition where the depth of the water is very close to a nozzle, so the air and water flow at the same time. And I calculate the effective density by the water and air ratio.
Okay.
Because for me, the air's momentum is basically negligible.
It's basically negligible.
Yeah. So only the water. So you can imagine that the air is taking the place of the water.
Why is it negligible? Because we saw in your only air experiment that it has a high acceleration.
I think the reason the air rocket could work is because of the area times the pressure difference. It's not because of the air's momentum.
It's not due to not due to the air momentum. Okay, but actually, if we have the air momentum, we have small mass. I agree with that, but we have high velocity. So shouldn't it be then considered?
Yeah, but the mass is just too small. I don't think it will be sufficient to actually lift it. I think the more effective force will be the area times the pressure difference.
Okay. So in your experiments, did you vary the nozzle radius?
I only varied for the thrust over time case.
Yeah, that's what you said.
Yeah.
And do you have the graph of that?
This one?
Okay. So actually, you did vary the size.
Only for the thrust force over time.
Okay, thank you. So let's now talk about the polytropic coefficient. Like you had it's near to isothermal, but couldn't you, in your theory, if you pump pressure into the bottle, what was the max pressure you reached?
You mean around 3 atm?
3. Okay. But wouldn't there be a temperature increase if you insert pressure into the bottle?
Yeah, I measured it. It's around like 2 degrees and 1
2 degrees.
in this case.
And actually, okay, but for calculating it, which temperature did you take? Because actually, if we pump air into the bottle, the temperature would like increase, but is also dissipated through the water and just the water bottle, right? Yeah. So which temperature did you take? After just moments after inserting the pressure, or did you wait some moments before taking the temperature?
Which part of the equation are you talking about?
I'm talking about the polytropic coefficient gamma, which I think is dependent on the temperature, right?
Yes, but I just experimentally determined, like, are you
And
talking about why is it like, can you rephrase your question a little bit?
I'm just asking which temperature you took, because if we insert pressure, the temperature changes, and you also saw it, right?
Yeah, no, but to calculate the PV gamma, I don't need the actual temperature for the equation.
What was the equation for to calculate?
Here.
So, right, here, okay. Yeah, okay. I was just wondering about it, because why would you say that an adiabatic process is not suitable for this problem?
So the first thing is this 1.4 is for like dry air. But I believe for my experiment, it's probably some water vapor is still inside. So I believe that's why it is like in the middle. So it's not like 1 or 1.
That's what I wanted to know about. Because if you have launch off, was there still sometimes water was still inside of the bottle?
Yeah.
Right. But did you see like any kind of vapor because of the air cooling down in the bottle?
As I remembered, I don't think I've seen it. Let me see the video. Yeah, I don't think it's that obvious.
No, when you launched it, and then
yeah, this is actually the same with launching, but it's just tied onto the stand. But yeah, I don't think I see any water vapor.
There was no water vapor.
Like not, I can't see it.
You couldn't see it. Okay, that was my question. So okay, now under certain conditions, was a problem statement. So can you just resume it? What are the certain conditions for this? Because actually we saw that there was an optimal air and pressure ratio. Water and pressure ratio. And like, okay, these were the conditions. So could you just?
Yeah. So I believe the initial force is actually the maximum. So when the initial force can actually overcome the initial mg, it could launch. So this is how this line is plotted. So the initial force is bigger than mg. This red dotted line.
Okay. Okay. Thank you. But what I wanted to ask is how did you determine the optimum, like the optimum of water and pressure?
So I find it experimentally. So
you find it experimentally and just took the max.
And I could actually estimate it by I believe like impulse to estimate the ratio is around like 0.3 to 0.35, and my experimental is like 33%.
What do you think would happen if you have only water in your bottle?
Obviously no air could be pumped inside, so you cannot launch.
You cannot launch.
Yeah.
I agree with that. Okay. Yeah. So just I think. Wait. I'm sorry. If we get back to the rocket equation.
Yeah.
Yeah. Okay. Do you think that is suitable? And
It is not suitable. Okay, see, I just proved it is not
and
suitable.
why?
Because it assumes V as is constant, while in a real water bar rocket it is not.
Thank you. The opponent, 1 minute for summary.
Okay, thank you for this insightful discussion. So first of all, we discussed the G effective in the theory, which I think is in the theory not relevant, but in my opinion, G effective must be considered due to the high accelerations. So next of all, we talked about friction inside of the bottle, and the reporter explained that he considered the friction by this experimental determination of the red beam's velocity. For the air jet, we talked about how this air jet was also relevant if we have small volumes of water inside of the bottle. Because if we have small volumes, then also air can get out very fast, and you have to include this in your theory. We talked about the nozzle diameter and how you varied it, but I saw like you had 2 parameters, so maybe you could have investigated a bit further on this, but it was enough for the thrust, I think. You talked about max pressure and polytropic
Thank
coefficient.
you very much. Question from the reviewer.
Yeah, so my first question is for the reporter, was sea loss assumed to be constant for all the losses?
Yes.
Okay.
For the same bottle.
Yep. Did you assume, go to slide 11, did you assume choke flow or not? Because I see the mention of subsonic flow also.
It depends. It depends on the pressure difference. When I believe the pressure is like if the ratio is over 1.9.
Yep. And how did you determine the point at which two-phase flow would stop?
Okay, it could be obviously seen in the video, as it would I just took it experimentally and know like what
And
time.
time for the two-phase flow was assumed to be constant across all launches?
No, it's it will be different on different cases. So yes, take
Okay.
it on video.
Yep. And on your for the opponent, do you think it is fair that the sea loss was assumed to be constant across all launches?
Across all of the bottle. No, I don't think so, because like if you have the geometry of the
Okay,
bottle,
thank you.
it is greater.
Yep. How did you measure the acceleration? Because I saw both static tests but also tracker videos. How exactly did you measure the acceleration?
Yeah, just tracker video.
So what was the point of the thrust versus time graph for changing nozzle diameter? Do you have acceleration versus time graphs for those also?
No, I did not see the acceleration over time for a nozzle. For a static launch, I just trying to see what is inside the bottle app. It is so I tied it onto a stand.
Did you use an accelerometer for any of your launches or
The what?
tracker?
The what?
Did you use an accelerometer for any of your launches?
What is that?
Accelerometer.
No, I just tracked it from video.
Do you think the tracker method is sufficient here, or should it?
If you considered the parallax error, I think
Yeah, I did.
Okay. I saw some grainy footage. Do you think the footage was of appreciable quality to be used as tracker footage?
Yeah, I think because there was a deviation which I don't think was not considered in your theory. A deviation from the horizontal axis.
What was the nose of the rocket made out of?
Plastic.
Okay. Yep.
Oh no! It's made out. No, the top part.
Yep.
Oh, it's clay.
Okay. Yep. Was the mass of the clay account for in your model?
Yes.
Yep. What is adiabatic heat loss? Just very quickly.
It is. What can you?
On the pie chart, you had 75% of it was adiabatic heat loss. What is that?
Yeah, to the temperature increase. The temperature and the heat going out.
Heat going out.
Yeah.
Okay. Yep. So you used the same type of bottle each time. You didn't vary the.
I did not vary the bottle because I think it would change a lot of coefficients. So I just tried to like find everything of a single kind of bottle.
Yep. Did you consider inertial forces within your rocket during launch in your model? So that is the acceleration of the water actually inside the bottle itself. Did you consider that as
No.
Do you think that should have been significant and accounted for in this model?
No, I don't think so.
Okay. Yep.
Okay, I think you're out of time.
Jason, and today I'll be reviewing problem number 14, water bottle rocket. So again, the problem, compared to a plastic water bottle partially filled with water. Under such conditions, the bottle is launched and flies into the air, and we are asked to investigate how the acceleration during liftoff depends on relevant parameters. Okay, so the report, the comparison of the report is that he identified the basic quantitative reason for launch. He identified a basic model using the steady-state Bernoulli equation, and a wide range of parameters was considered, and I like that he considered the shape of the model profile itself, and some stability analysis was done, and I think that was good. And furthermore, he modeled the two-phase flow at the tail end of the water phase. However, he didn't strongly explain qualitatively why each section of the acceleration versus time graph looked as A. Why was it increasing during the water phase? Why was it decreasing during the two-phase flow period? And he also ignored inertial effects and apparent gravity, and I think that was a big flaw in his model. On the practical side, I like that he determined his own drag coefficient, and I like that he determined the profile of the bottle himself. However, I question the validity of his setup. He used a bike pump to pump air into the bottle. The bike pump gauges are known for being extremely inaccurate, and also it limits the range of pressures for his launch. I think that was a limitation. On slide 28, you can see some very grainy video for the tracker footage, and I don't think that was necessarily sufficient or accurate. And finally, it was unclear whether the nozzle tests were done statically, and later in the clarifying question, he seems to have said that no acceleration versus time graphs were actually produced for changing nozzle size, which I think questions the relevance of those nozzle diameter changes to the plot. And other weaknesses, he didn't qualitatively explain why the polytropic constant is lowered. I believe it is due to condensation, but then at the same time, he also said that condensation was not observed in his bottle. The initial conditions of the bottle, how exactly was the first second of liftoff determined was unclear, and also that the same goes for the model. It was unclear whether the initial velocity of the water was considered to be 0 or at the steady state Bernoulli equation already. Failed to consider failed to consider changing different flow regimes with increasing fill. I'll get into that in the missed points. And I thought his angle analysis was flawed, and I'll get into that in the missed points. And I think assuming that C loss is always constant, even if the bottle diameter is changing, is another big flaw. I'll get into that in the missed points. So for the opposition speech, in general, identified the strength in the series quite well, but brought up some irrelevant points like how the ideal rocket equation was used. I think that was just used to demonstrate that we need a more complex model. On the practical side, and did identify many of the weaknesses in the practical that I personally agree with, which was good. So on the points discussed, the G effective acceleration opponent noted that this is significant. Reporter said it's not, and that only the normal G was used. I believe it is significant with calculation down here with his values, 400 meters per second, 3 bars. If we quickly assume that water interface is around 10 centimeters, then we see that the increase in static pressure from the G effective is like around 20% of the overall pressure in the bottle. Frictional losses was mentioned. I think it is fair that the opponent covered it in C loss. However, again, I think C loss should have been changed with changing nozzle diameters and changing bottle geometries because, again, the boundary layer growth in this problem, for smaller nozzle diameters, you obviously get a higher C loss just because the boundary layer is a bigger proportion of the overall diameter of the bottle. With the effect of air momentum, I generally agree with the reporter here. With the opponent here, I think the airspeed is quite high considering the high pressures, and the moment of the air should have been considered. And with the polytropic exponent gamma, I think I agree with the opponent here. I think it should have been changed with the differing initial temperatures and initial conditions. And the reporter again didn't qualitatively explain why it was lowered. It is due to condensation, and yeah. So again, the points missed, the effective acceleration, the angle analysis fails to recognize that the effective acceleration means that the angle would interface will still be perpendicular to the bottle. The full experimental setup should have been discussed more. And
final remarks of the reporter.
Okay, so hi, I'm a reporter. I'm here to do my concluding remarks. So the key mechanism for the water bottle rocket is about the conservation of momentum. And I have considered a polytropic process and using a Bernoulli's equation. And the center of mass and the center of pressure position affects the stability of a rocket. I've also investigated maximum height by integrating below the curve using Euler's method, and the drag coefficient is solved using CFD. And the C loss and gamma is obtained by the static experiments where it's able to determine the coefficient experimentally, and the thermodynamic loss is around 76%. So the parameters I varied in my experiment, for nozzle diameter, I've only investigated for the thrust force over time, and I did not date for the acceleration experiments. And for initial pressure, we see a faster exhaust and causing a higher burst. For water volume, we see it will be optimized at around 33%. And the launch angle, it will affect the water's level inside the bottle, and it will cause its decay time. And the center mass will affect its stability, and also investigated the launch conditions mentioned in the problem statement under certain conditions. Now for discussion. So the nozzle radius is considered in the exhaust force, where I consider it theoretically. And I have a control release with a handle which is built instead of with the launcher. And the temperature is around 2 degrees change, and I have experimentally find it. And the C loss is accounts for the geometry of the bottle. We have fixed the ideal rocket equation to see what is the difference between a water bottle rocket and an ideal rocket. And the G effective is irrelevant due to the acceleration with the bottle. So the water is accelerating with the bottle, so I believe the G effective could not be considered. And we also have the mixed exhaust space in the liquid transform, and the air drag from CFD is in the CFD wind tunnel for Navier-Stokes equation. And the air density is very small, so it is negligible. And I want to clarify again, the added back, the heat loss is, I mentioned, is the thermodynamic heat loss, which is the 76%. And the bottle geometry is not changed because the C loss is constant. And this is the end of my.
Thank you. Questions from the jury?
I would like to ask the reporter, can you recall the frame per second of your camera, the speed of your camera?
240.
240? Thank you so much.
Maybe I could ask an opponent a question. So could you go to the slide showing tracking of the rocket? Any slide.
Is it?
Has it?
Yeah.
In the observation? Or
Like the one where we can see
Oh, yeah.
tracking.
28. 28.
I think it's
Can press 20.
this one.
So here, order of magnitude of the acceleration is 250, right?
Yes.
And how many frames do you have per second? 240.
240.
Do you think that's enough time resolution to apply this method to calculate acceleration?
Actually, I don't think so. I think that high frame rate per second would be much more effective, but this is limited, I know. But actually, yes, I think high frame rate would be necessary at this high accelerations.
Yeah, I'd like to ask the reviewer, you have mentioned about the thrust as an important factor. They have shown on the slide the value of thrust. Did you notice that value?
Pardon?
Did you notice the maximum value of thrust they have presented on the slide?
I did not remember the maximum.
Yeah, could you go to
I think we have to have short questions. These are no more short questions. This is more.
It's like showing the value on the slide, so I don't.
But this is not a question to the reviewer. No.
Yeah, but if we were to answer that question,
Okay, go
has
quickly to
see.
that slide.
Yeah, there is a with a value of trust over the time.
Sorry,
You have the trust value over the time. You measure that and model. So
I think what you're getting at is that method is inaccurate for measuring the acceleration versus time. Because the
yeah.
mass
Oh,
of
that
the
one
bubbles-
over here. Have a look. Yeah, you have a trust. Can you use that value to calculate the acceleration?
No, you need to consider the bottle's mass itself as water is leaving the rocket.
Okay. Thank you
That's
so
why
much.
it's insufficient.
Question to report is Bernoulli applicable in your model for this situation?
I have estimated the Reynolds number are quite high. It is a turbulent loss, so it's not like the normal use for Bernoulli, but I have considered the C loss.
Okay. Are there any further questions? Well, if there are no questions, I don't think we have to extend it any further. Thank you all, and we will proceed to grid.
Thank you.
Okay, then I ask you to show me the grade for the reporter, please. Six, 7, 8, 5, and 7. Next, the grade for the opponent, please. 6, 7, 8, 6, and 6. And lastly, the grade for the reviewer. 6, 8, 8, 7, and 7. For the report, we have an 8 and a 5. Let's start with the 8.
Okay, yeah. So, first of all, I will let you know about the partial grades. So we have this 1.5 for the report and 1.75 for the discussion with opponent. So the presentation, in my opinion, has all the important things in it. You have presented it quite well, and you also varied the parameters. You did some own contribution to that work. I also have that you put some measurements that was not so obvious. You calculated the different values of the acceleration. You model it and compare with the modeling results. So comparing also to my previous grades I was giving to that tournament, it was of that high value. So I'm quite convinced that this is a good mark for me.
Okay. We also have 5.
I have a 5, yes. My overall grade was between 5 and 6. I was, and I rounded down because I'm not quite sure that we can really trust Tracker to calculate the accelerations very well. So I wouldn't overtrust that, the numbers for the acceleration. It's a double differential scheme for a very short period of time, and there is and the images that were being shown seemed a little blurry. So I wouldn't overtrust, Tracker to be able to actually track the points properly. So. I'm pretty sure that you did a good care and effort in studying the problem, and you had plenty of good work there, and I'm pretty sure that you had a lot of fun. But nevertheless, you have to be a little more skeptical about these kind of numbers, and you have to verify them against measurements with accelerometers and other ways, so as to make sure that for that very short period of time you don't get misled by inertia of the calculating. Otherwise, congratulations on a good effort. I was between 5 and 6 and eventually rounded
Do you
down.
give them partial grades?
Partial grades, yeah, 3.7.7.
Okay.
And I was hesitating about the remaining 5.
For the opposition, let's also start with the good stuff first, the 8.
Yes, and again, although the presentation, in my opinion, of the reporter was quite good, you were able to bring some important issue, especially this effective G, and comparing this to the value of the measured acceleration. I also wrote down that you were talking about the trust, the number of points for your discussion nicely in line with my opinion. What would I asked the reporter, so my partial marks was 1.5 for the questions, 3 for the opposition speech when you really put all the good information, and discussion with the reporter 2.25, so it sum up to 8.
Okay, I was one of the 6s. I can maybe briefly comment. The main issue for me was in the discussion. The first 2 minutes were fantastic. You started with the effective G, then he said it's small, then you jump to the correct slide where you see that the G is where the acceleration is very large. Fantastic. But you did not do anything out of it. And I think that was the thing during the whole discussion. You asked, you raised good topics, you asked the right questions, but you too seldomly actually stated your opinion and you left him off the hook very easily at that segment, for example. You just went to the next one, but there he said something which was really odd, like a contradiction, but you just left him off the hook, and that was a bit frustrating. So it was really the own opinion presented during the discussion part, which really suffered. So I gave you 125 for the questions, 2 for the opposition part, and 125 for the discussion. Good. For this review, we also have 2 8s. Maybe Luca.
Yeah, sure. So, first of all, good job. I think you did really systematic. You reviewed this whole process in really systematic way. You gave enough attention to all of the relevant points for both other teams. And the most important thing for me is that you are the first team that grabbed the biggest problem and started talking about it, and this is this tracker thing, this methodology of calculating acceleration. So I was really glad that you did that. That's it, and maybe my grade would be even higher if you started a discussion on this gamma coefficient of polytrope, but let's not go too deep into that. So that's it from me.
If I may just
partial grades for it?
Yeah, sure. So I gave you for your questions 1.25, for review of the report 3.25, for review of the opposition 1.5, discussion of analysis 1.5, 0, and that adds up to 8.
If I just add one word concerning your calculation, showing us that the effective G is really
very good.
Yeah, so that was
Very
also something that I took into account giving the grade.
I was a 6, but that's not to say it's a bad review at all. I think I followed the score sheet, and I think I have the problem with, as with most reviews, is that the review of the opposition is, if I follow the score sheet, is very brief, and then that's where you basically lose the points. So in that segment, you only got 0.75, and I think that is a bit the problem. I mean, you had a good thing on the report. The questions were also good, so I got 150. What I don't like but this is a small thing, is you have a lot of text in your slides, and I don't think it's necessary you to go through all the points and read out all the text. If you just prioritize a bit better, for me, I'm very happy to give you a higher grade. So I gave you 150 for the question, 150 for the report, 0.75 for the opposition, and 125 for the discussion. Okay, any questions from the teams? No? Alright, then we will have another 10-minute break. Could you please rearrange? And also we will again have 1 minute preparation space for the reporters, so maybe already get ready during the break.